Maybe I'll be honest. There we go. Sorry.
Also, what's strange about that phone is that occasionally when you turn it on, it says you have a new message, but it's not part of any plan at all. There's no reason for there to be a message on there. All right, so 2D, we have that the angle is equal to, for the entire circle, so this is for the entire circle, 2 pi radians. So we're going to set up something similar here. So first off, what is the surface area of a sphere?
4 pi r squared.
Yep. And so when we're talking about solid angles, so imagine you've got this ball here, and you got a ball, and from the center, you're sort of projecting out into a 2-dimensional surface. And so let's see how well I can draw that. The center here, and it projects out onto something like that, where this is on the surface of the ball. That this angle right here, this solid angle, as opposed to angle for 2 dimensions, this solid angle, if the patch right here, if patch on surface, is the radius by the radius. In other words, this is, so we have a 2-dimensional, which is r by r. Then the angle is 1 steradian, which is abbreviated as 1 SR.
So lumen per steradian.
Yes. So this becomes lumens per steradian, which is known as a candela. Which actually is a base unit. Is or was, they changed what we consider standards, but candela at one point was a base unit. So if I've got this bulb over here that is producing light specifically at that wavelength, that is producing it in all directions, I can figure out what the luminous intensity is of the entire bulb. So if this is isotropic, I guess that's the description of the bulb. If isotropic, in other words, the same in every direction, then my luminous intensity will be 476 lumens divided by 4 pi steradians, and whatever that is, 37.9 candelas. Now, typically, it doesn't really help a whole lot to know what the luminous intensity is in every direction, so let's concentrate on something a little bit different. Questions up to here?
What is the, so 476 divided by 4 pi steradians, what is the steradian value for that? Like, I don't, we get it.
I was assuming that we have this 476 lumens of luminous flux that is going out in every direction. So I basically wanted to figure out what it is for the entire sphere. So the 4 pi steradians represents the the solid angle for an entire sphere. We're about to do one that is less every direction.
Okay.
Is that sufficient for now, or?
No, we'll
Okay.
circle back.
All right, sounds good. Bring it back to the solid angle. So if I've got my little patch here of r squared, and it's 4 pi r squared around the whole thing, that's why it's 4 pi steradians for an entire sphere. Just like over here, I know that my arc length is equal to r theta, so my angle is equal to my arc length over r squared. Oh, sorry, over r. Over here, the solid angle is going to be the area of the patch divided by r squared. So if I have a patch here that's 2r by r, in other words 2r squared, then it's 2 steradians. So this is just a generalization for a number of steradians. Keep that. Here it is. Let's take it to the next step. The spotlight. And use the numbers I got going already. So suppose I have a 60 candela bulb. So this is an idea of the amount of, with our candela, so it's luminous intensity, it's an idea of, we can get how bright it is, because I know this is my luminous intensity, which is the luminous flux divided by the solid angle. So my luminous flux here should be 60 candelas. Since this number here is for light going in every direction, my solid angle would be 4 pi steradians. So my luminous flux is 240 pi lumens, not illumines. Which is somewhere around 750 lumens. What I'm going to do is I'm going to take this bulb that's giving off light in every direction. Since it's a spotlight, I really want to be able to focus it, so I put mirrors on one side of it, so any light coming off the back side is going to be shot forward. And so I'm going to take my bulb here, put something around it, so that all the light ends up shining onto a 19 square meter section. Not drawing the scale. And again, just so that I don't have to worry about coming up with crazy numbers here. So basically, I have a spotlight, I turn it on, it's giving off 240 pi lumens in every direction, but I have mirrors and things like that in order to reflect it all into one direction. What is the luminous intensity here? Well, going back to that, because we've concentrated in a single area here, my luminous intensity should be a lot much greater. So I've got the total flux there, 240 pi lumens, divided by whatever the solid angle is there that's projected. we go to this formula right here. I know my area is 19 square meters. The radius, that's the distance from where the bulb is to where it's being projected. So this is 40 meters squared. So I end up with 19 over 40 squared. Which is?
0.011875.
Units?
Steradians?
Yep. Notice my units over here, the meter squared up here, and this meters is being squared in the denominator. The meters are gonna go away. And so, similar to radians, it's a unitless unit. .01875 steradians. And we end up with a final luminous intensity.
63,493.241.
Units?
Candelas?
Yep. And so we, obviously, it's got like much more intense than if it were just in open air. Or naked, whatever term you wanna use there.
Basically, if that cone wasn't there reflecting all that light back, it'd be much lower.
Yeah. All right,
That's insignificant.
let's change it up one more time.
That's like,
So my image right here is I basically have a bulb, I got the shield behind it in order to reflect it all, and then I've got a flat wall sitting over there. Suppose that flat wall is not flat. In other words, I have my bulb here, shining light out onto a wall that's tilted. Let's still keep it 19 square meters. I do need to give that angle right there. Let's make that say 30 degrees. Yeah, make that 30 degrees. So my light's being spread out over a far larger surface here. Hold on just a second. I need to resolve this in my head first. And this just popped up in my head. Yeah, there's a problem here. Nothing wrong with what we've done, something wrong with what I was about to do. Oh, okay. No, okay, it works. All right, I'm back. So recognize if this is 19 square meters here. On the tilted surface, this angle here that the light is coming out at has to be smaller. Because if this were the 19 square meters, then yeah, that's what we just did. But because I tilted it out, if this is 19 square meters, I have to narrow the beam. So if I imagine I'm drawing something like that, hitting a surface there, and it's some area, if I tilt this surface right here, to get the same area, this area here would be the same as that area there. So it is a smaller angle. It is more focused. So how do you actually deal with that? Well, a little bit of trick. That's a 30-degree angle. What we care about is the part that is perpendicular to the light, to the way the light is coming in. And so this would be 19 times the cosine of 30 degrees. So my solid angle now changes. Because we have to take that angle into account. And so we can make it an even more general formula for solid angle to be the area times the cosine of that angle there over r squared. So in this particular case, it becomes 19 square meters times the cosine of theta. Which is 30 degrees in our particular example. And so now this becomes 0.00 something.
Is it 40 meters from the light to the bottom of that triangle there, or the perpendicular, I guess?
Then technically it would be, the crude approximation, it should be roughly to the middle there.
Okay.
I'm not worried about the difference considering 40 meters versus something that's basically 4 meters by 4 meters.
Okay.
So
we still just use 40 meters for the
yeah,
solid angle?
yeah.
Okay.
I got 0.0103.
103 steradians. And so my intensity, 0.103 steradians. We get, oh, wait.
You sure about that there?
I thought I did it right.
Do you have your calculator in radians?
No, that's fine. It's in degrees.
No, it should be in degrees.
Oh, yeah.
Cosine 30 degrees.
Yeah, 19 cosine 30.
Yeah.
19 cosine 30, I got about 16.45
squared.
divided it by 40 squared.
Yeah, I forgot the square one.
Okay,
Okay.
so we're back to,
Yeah.
you got it, Aaron?
I did.
So what's the luminous intensity?
It is 73,315 lumens.
What was your unit?
Oh, sorry, CD.
Candelas.
Candela. So it is.
So in order to hit 19 square meters, we had to narrow the beam some, which made the luminous intensity greater. However, this has brought up another thing. The fact that, depending on what the purpose of your light is, but as the light's coming in, yeah, it tells us an idea of the amount of light within this cone here, but it's striking a surface makes a difference. Because oftentimes you're trying to, on the spotlight, you might be trying to highlight something. So what you care about is how much light is actually hitting the surface itself. And so we have yet one more vocabulary word. Illuminance. And so let's get rid of some stuff. That, and the textbook does not have this in it. Luminance. The memory trick, the Illuminance starts with the letter I. This is the incident light. Luminance starts with the letter L. This is the leaving. So illuminance deals with the amount of light that's actually striking the surface. Luminance deals with the amount of light that bounces off of it. Whereas luminous intensity is the luminous flux per angle, or solid angle. This, which the book uses a capital E for, because we're not using that enough, is equal to the luminous flux per area. And so my units here, the SI unit of my illuminance would be the SI unit of luminous flux divided by the SI units of area. Lumens per square meter, which was too much for them to write. This is the lux, abbreviated to LX. So in my spotlight example, assuming that light's not bouncing off of air, we're making some assumptions of no loss here. So we have my light shining over this solid angle here. This is the number of candelas. No matter how far out I go, assuming there's no loss, this will stay the same. Because the luminous flux coming from the bulb, I'm assuming the bulbs that last forever, over that solid angle, that's not going to change. However, as you get farther and farther away, the area that it's hitting gets bigger and bigger. So the luminance will get smaller with distance, but the luminous intensity will not, in our nice ideal world.
What did I? Oh,
I understand. Because as you go the area increases by, you're taking out into account some people. And then if you don't care about the distance, you just care about
All right, so I have that. All right, so E, so my illuminance, which is F over A. F is my luminous intensity times my solid angle over A. My solid angle, right here, so this becomes I times A cosine theta over R squared over A. Area cancels out. And so we have I cosine of the angle over R squared. So if the light is normal to the surface. And what do I mean by normal?
You mean that it's at that yellow green?
No. Different meaning of normal. This normal is a math term. In 131, normal force. Why was it called normal force?
Explain why it's called that.
I was thinking about something else.
Yeah.
Alright. Normal means perpendicular.
I was not.
Sorry, I cut you off, Susan.
No, I wasn't gonna say it, but that's back of the head thing.
Alright. So. Perpendicular. And someday I will spell correctly. So if the light's hitting smack on into it, then our angle is 0 degrees because the wall's not tilted, it's straight up. And so my illuminance would be just I over R squared. Get this up a little more.
Equals I over R squared.
And so just a quick plug and chug example, I got a 100-watt bulb. With a luminous intensity of 120 candelas. Sorry, let's make that 100 candelas because there was on 120. You know what, these days I'll learn that my memory is heavily flawed. 120 watt bulb, 100 candelas. And I'm shining it down onto a surface that is 2 meters by 2 meters. Then my illuminance is just going to be 100 candelas over my area of 4 square meters. And we get 25 lux. And that's pretty much chapter 34, 33, chapter 33. Questions to hear?
Wouldn't that be I over A though, instead of I over R squared? Are we assuming that it's 2 meters away?
It's,
'Cause
oh,
we have the illuminance is F over A.
yeah, no, you're right, you're right. I mixed the formulas in my head. So I got my bulb here, and this is 2 meters away, thank you. So then it's 2 meters squared. All right. So I think a big question right now is how much do I expect you to know? I mean, obviously, made several mistakes. I had the point where I had to resolve it in my own head. You know, let's go for it. Let's do a quiz on it. Not right now, but. You got a test on Monday. Where are we? Over here. I don't, yeah, let's go for the Monday after that. So March 1st, the quiz on 30. I'm trying to remember how many test questions I had at the end of last semester on this chapter. I don't really remember. It would have been simple stuff. But you're so much better than those hacks I had last year, so you guys should be able to do a whole lot better. Absolutely easing my way into this stuff. Probably the fourth time I teach this class, those people are going to suffer greatly at this. All right, questions? All right, reflection. So, mirrors and reflection. The big thing to know for reflection, so this is chapter 34. So if I have a line that's normal to my surface right here, if I have light coming in at this angle right here, it should reflect back. So this is the angle of incidence and the angle of reflection. So if it's a very smooth surface, then it's very clear, angle comes in, light goes out. If it's a bumpy surface, as light comes in, it's not necessarily, the angle of incidence depends upon the surface where it makes contact. So this light will probably bounce straight back. Light that passing this way will probably bounce like that. So if I have a rough surface, it's not going to reflect as evenly spaced. But we're going to assume mirrors, ideal mirrors,